let's say we have the system x prime equals 6x minus y prime equals 5x plus 4y. Okay, we'll go ahead and treat this just like we did yesterday. So we'll go ahead and find the eigenvalues of the matrix of the coefficients. So 6 minus lambda, negative 1, 5, 4 minus lambda, take the determinant. We get lambda squared minus 10 lambda plus 24, but then we're going to add 5 to that. So that's going to give us plus 29. Set that equal to 0. We're not going to be able to factor it. If we go ahead and use the quadratic formula, you can take my word for it, you get complex eigenvalues. Okay, so again, proceeding just like before, let's call lambda 1 equal to 5 plus 2i. We're going to go ahead and solve a minus lambda 1i, augmented with 0. So that turns into the matrix 6 minus 5 is going to be 1, and then we're subtracting 2i, negative 1, 5, and then we do 4 minus 5 plus 2i, so we get negative 1 plus 2i. I'm sorry, negative 1 minus 2i. And this gets augmented with 0. Okay. And if you haven't noticed already, when you cancel out the bottom row by multiplying 5 times row 1 minus 1 minus 2i times row 2, you get a 0 here. You are going to get this second term to also equal 0. Now all we're left with is 1 minus 2i, negative 1, and 0. So if we solve for k2, we get that k2 is going to be 1 minus 2i times k1. So our first eigenvector, if we let k1 equal 1, then k2 is just 1 minus 2i. Okay. And now if we go to the second eigenvalue, 5 minus 2i, again solving a minus lambda 2i augmented with 0. Now we get 1 plus 2i here, and negative 1 plus 2i here. And if you do the same procedure as before, take 5 times row 1 minus the quantity 1 plus 2i times row 2 to get a 0 in the bottom row. This will go to 0, this will go to 0. And we get pretty much the same relationship we did before. The only difference is that k2 is now equal to 1 plus 2i times k1. So then our eigenvalue, or eigenvector, if we let k1 equal to 1, then k2 is just 1 plus 2i. Okay. So currently, our solution for x is going to be C1 times our first eigenvector times e to the whatever the eigenvalue was, so that's 5 plus 2i times t plus C2 1 plus 2i e to the 5 minus 2i times t okay. So we'd be done, but we're stubborn. We don't like having imaginary numbers in our solutions. Okay, so what we're going to do is pretty much similar to what we did earlier in the year. We're going to try to rewrite these in a manner so that we don't have any imaginary answers. And we can do that pretty easily since we have conjugates here. So if you notice that the bottom part of the eigenvectors here are conjugates, we'll do it this way. So we'll let K1 let's do K1e to the lambda 1t. You know what? This is going to get confusing. Okay, at this point, I'm going to drop the vector notation. You'll see why in a minute. So when you see K1 floating around in here, it's going to represent the eigenvector. Okay, so we'll let K1 e to the lambda 1t be one of the answers. So that'll be this one right here. And a good way to describe the second solution then would be to use the notation K1 and then put a little bar over it, which means conjugate, e to the lambda 1t. So let these be the solutions. We do not have to put a bar over the lambda. I mean, we could. You know what? Oh, you know what? We probably should. Because otherwise I would have called it lambda 2. You are right. Good catch. Okay. Okay. So let these be the solutions. And now what we're going to do is we're going to go ahead and try to find the solution in terms of real functions. So we're going to let lambda 1 in general be alpha plus beta I. So that now K1 e to the lambda 1t, if I plug in the eigenvalue into the exponent and split it up, we get K1 e to the alpha t times e to the beta t, or I beta t. And what we're going to do is pull out the real part along with the eigenvector. So we'll have K1 e to the alpha t. And now what we'll do is replace this guy using Euler's formula, which gives us cosine beta t plus I sine beta t. Okay. And then similarly, if I look at the conjugate solution, the only thing that's going to change is we're going to have cosine beta t minus I sine beta t. Okay. So now what we're going to do is a little bit of algebra here to try to eliminate some of the imaginary terms that we have. So what we'll do is take 1/2 of k1 e to the lambda 1t and then add its conjugate so that now we get 1/2 k1 plus the conjugate of k1. So I'm just adding these two things together and grouping the cosine. So e to the alpha t cosine beta t. And then, let's see, here what we'll do is factor out an I and make it negative. So I over 2. So we get minus k1 plus k1, the conjugate of k1 anyway, times e to the alpha t sine beta t. So adding these two expressions together and then factoring out 1/2 k1 plus k1 conjugate, and then doing the same thing with the sine term, but factoring out a negative I over 2. This becomes minus k1 and then plus k1 bar. Okay, now what that allows us to do is look at these and have real coefficients now. Okay. And now if we do the same thing, let's do I over 2. So we're starting with this to get this weird solution, and then we're going to do I over 2 minus k1 e to the lambda 1t plus k1 e to the lambda 1, the conjugate of that, times t. So these are the two expressions that are going to be the key to eliminating the imaginary part of the solutions. Okay, and now doing the same thing as before, we'll group the cosines and the sines together. So we're going to have I over 2 and then minus k1 plus k1 bar e to the alpha t cosine beta t. Now I'll have plus 1/2 k1 plus k1 bar multiplied with e to the alpha t sine beta t. Yes. Yeah. Okay. So if you're wondering why we're doing this and that, the key is that these coefficients are real. Okay? if you take half of k1 plus the conjugate of k1, well, when you add the two conjugates together, you're going to get 2a essentially, right? Or alpha in this case, because you have 2 alpha, and then you're going to have the minus beta I plus the beta I cancel out, so you're just going to get a, okay, or alpha, sorry, used to pre-calc. So this is going to be real, and then if you do the same thing with this term, this coefficient, this is going to produce the coefficient of the imaginary term, which is beta. Okay? So the whole point of doing this calculation is that now we have cosine and sine terms, but even though these coefficients look imaginary right here and here, if you actually do the calculations and do I over 2 minus the eigenvector of k1 and then add the conjugate of that, you're going to get just a coefficient that's real. Okay? You'll get just the coefficient of the imaginary term of the eigenvalue. Okay, so what we're going to do, let's write this down. So now all coefficients are real, and we're going to call 1/2 k1 plus the conjugate of k1, we're going to call that eigenvector b1, and we're going to call I over 2 minus k1 plus the conjugate of k1, we're going to call that eigenvector b2. This was simply the real coefficient, or the alpha, of the eigenvalue. And this is simply the imaginary coefficient, not the imaginary number itself, but the coefficient of I. Okay? So let's put everything together. Here's our final theorem for this situation. To find real solutions corresponding to complex eigenvalues, if we have lambda 1 equal to alpha plus I times beta, and let's say that's an eigenvalue, bless you, of the systems that we've been solving for the past few days, x prime equal to a times x, and if b1 equals half of, and now I'll be using the complete notation, eigenvector k1 plus the conjugate of the eigenvector of k1, and then b2 will equal I over 2, and then this will be minus k1 plus the conjugate of k1, then x1 equal to beta 1, or b1, sorry, cosine of beta t minus b2 sine beta t, all times e to the alpha t, that's this first combination of terms that we have up here, and x2, which will be b2 cosine beta t plus b1 sine of beta t, all times e to the alpha t. That was the second one that we wrote here, just writing it in the new format. Okay. Then we say that these are linearly independent solutions of x prime equal to ax. And I like to use this notation to maybe make life a little easier. If you simply remember b1 as the real part of k1 and b2 as the imaginary part of k1, this will help you keep track of what you need to put where. Okay? So when you're writing out the solution, this simply means look at the real part of the eigenvector, that's the coefficient here. Look at the imaginary part of the eigenvector, and so on and so forth. Okay, so as weird as this looks, writing the solution is actually not very painful at all. So going back to the example from before, we had lambda, which was equal to 5 plus or minus 2i, right? Which led to, well, you know what? Let's do it like this. Let's just do the first eigenvalue, which was 5 plus 2i. And that led to the first eigenvector, which was 1 and then 1 minus 2i. So we had this eigenvalue, which led to this eigenvector. And from here, we can write the solution. X is going to be C1, and now we'll use exactly this pattern here, times the quantity of, and again, B1 is just the real part of your eigenvector. So if you look at this vector, what's the real part? Literally. 1 for the top, and then what's the real part of the bottom? Cosine beta, what was it, 5 plus 2i, so beta would be 2, minus, and then this again, B2 is just the imaginary part of the eigenvector, literally. So for the top part of the eigenvector, we didn't have an imaginary portion of it, but the bottom part, the imaginary part, was negative 2. Okay? And then that's all times e to the alpha, so 5t. That's the first half of the solution. And now we do C2, and then we follow this pattern. B2 is 0, negative 2. Cosine 2t plus B1, which was 1, 1. Sine 2t, e to the 5t. So here is our final solution. This solution is the solution to the example that we started with, but now this has no imaginary portion to it at all. Okay? As far as derivation is concerned, you don't really have to worry about it. What you need to worry about more is here. And this is probably useful. At least I think it is. Okay? So as long as you remember how to construct the solutions when you have complex eigenvalues and what these B's refer to, then you'll be in good shape. Okay? Alright, we should have enough time to finish. So, this takes care of all the scenarios where you have distinct eigenvalues, which means for a 2 by 2 system you have 2 different eigenvalues, 3 by 3 we have 3 different ones. We have yet to discuss systems where there's only one eigenvalue that's repeated. So we'll go through that, and then we'll be officially done with diffie-q. Okay, so for repeated values, there are 2 scenarios, and we'll go through one of each type. For some n by n matrices, A, let's call it, you may be able to find m linearly independent eigenvectors, which we'll call k1, k2, all the way through k sub m, corresponding to lambda 1 of multiplicity m, which may be equal to the dimensions or the size of your system, but maybe less than. This is the ideal scenario. Somehow you get lucky and you have one relationship that would give you 2 linearly independent eigenvectors, then you don't have to do any more work. Okay? Doesn't happen often. The second scenario is where you have multiplicity of the root, but you only get one eigenvector from it. So if only one eigenvector corresponding to the eigenvalue lambda 1 of multiplicity m can be found, then m linearly independent solutions are written as follows. Your first solution would just be your eigenvector times, and we'll call that k11, times e to the lambda 1 times t. Your second solution is going to be k21 times t e to the lambda 1t plus k22 e to the lambda 1t. If we have m of them, then we'd have k sub m1, and then the pattern is going to be t to the m minus 1 over m minus 1 factorial e to the lambda 1t plus k m2 t to the m minus 2 over m minus 2 factorial e to the lambda 1t, and so on. K m e to the lambda 1t. And I'll explain via an example exactly where all these, because I mean this is really what you have to pay attention to, is where these eigenvectors are coming from. Okay? All right. So we'll do one example where we luck out, so to speak. And then we'll do another one where, even though we have a multiplicity of m, in that case it'll be 2, where you really don't have any other choice but to kind of follow this algorithm here. Okay, so let's say we have the system x prime equal to, and let's just already write it in this form, 1, negative 2, 2, negative 2, 1, negative 2, 2, negative 2, 1 times x. And let's just pretend like we don't know that this is going to happen, so we'll treat it like usual. Find the determinant so we can find the eigenvalues. So the determinant of 1 minus lambda, negative 2, 2, negative 2, 1 minus lambda, negative 2, 2, negative 2, 1 minus lambda. Should I save us the time? By algebraic manipulation, we get this. By the way, this worked for me on an exam in college one time when I was doing a proof and running out of time, and I kind of knew what was going on. I put by algebraic manipulation. I didn't write BAM, and then I actually wrote out so it looked like I knew what I was doing. Got full credit. Okay, so by algebraic manipulation, etc., at some point you get this. Here's the point. We have a repeated value of negative 1 for one of the eigenvalues. Okay, so let's start with that. So for lambda 1, which is also the same as lambda 2, which is negative 1, let's see what we get there. So plugging in negative 1, which is essentially adding 1 to the diagonals. So I'm going to do that first. Adding 1 to the diagonals, and then everything else is the same. Well, this is nice. If I add these two rows together, you eliminate the third row. And if you add row 1 and row 2, you eliminate the second row. And if you just multiply through by a half, you get 1, negative 1, 1, 0. Okay, so what does this tell us? This tells us that K1 minus K2 plus K3 has to equal 0. Or in other words, we could say K1 has to be K2 minus K3. So let's see what happens. If K2 is equal to 1, K2 is equal to 1, then what is K1? Well, I guess I should probably pick a value for K3, right? What's the easiest thing to do? Let's make it 0. So then what would K1 be? Okay? So there's an eigenvector. What if we let k1 and k2, whoops, not eigenvector. What if we let k1 and k2 be the same? If k2, is that what I meant to say? No, it's not. What I meant to say was k2 and k3, so that now if these two are the same, what's k1 always going to be? That's 0. And what's the easiest choice to make for k2 and k3 then? Let's just make those both 1. So now we get this other eigenvector. So this relationship holds for this eigenvector and this one. And these are linearly independent because it's pretty clear to see that this is not a multiple of k1 and vice versa. Does that make sense? So that's actually good news because we don't have to do a whole bunch more work to find the other one. The only thing we have left to do then is go to the third eigenvalue, which was 5. And if you're okay with this now that we've done this so much, eventually you get that k1 has to equal k3 and k2 has to equal minus k3. So I'm bypassing all that stuff because we wouldn't finish the section and I want to get it done today. So sorry about that. So then the third eigenvector, if I just let k3 equal 1, I get 1, negative 1, 1. Okay? So then the solution for this example, which we kind of didn't work completely through, but enough to at least give you some insight as to what to do with the problem set for homework. You get C1 times 110 e to the minus t plus C2, second eigenvector, which was 0, 1, 1, and that was the same eigenvalue, so e to the negative t again, plus C3, and now our third eigenvector, which was 1, negative 1, 1, and then e to the 5t. So here's our solution for this scenario. All right, we can do this. 6 minutes. Are there any questions on that example? Okay. So let's do this one. X prime equal to 3, negative 18, 2, negative 9 times x. Again, we'll start solving it, finding the determinant of 3 minus lambda, negative 18, 2, negative 9 minus lambda. Again, we'll cut to the chase. Eventually you get down to a polynomial that factors as lambda plus 3 squared. So here we have a eigenvalue of multiplicity 2 and no other eigenvalues to work with. So we're going to go ahead and start solving. The augmented matrix A plus 3I with 0. So just add 3 to 3 and negative 9. We get 6, negative 6. Everything else is the same. Not very hard to see that row 3 is exactly a third of row 1, so you can eliminate that easily. And then if you multiply by a sixth, you get 1, negative 3, 0 for the top row, which tells us that k1 has to equal exactly 3 times k2. So our first eigenvector, if I let k2 be 1, I get 3, 1. So far, I have one solution, which is going to be 3, 1 e to the negative 3t. So now we're working through this second scenario. So I found one solution, and now I'm going to kind of have to work my way down here to find, in this case, I only need one more, so I don't have to go very far. And now here's how you do that. So to find x2, you're going to solve same matrix, A plus 3I, but we're going to call these new entries, instead of K1s, K2s, K3s, we're going to call them P's, so P1, P2, and so on. And we're going to augment that not with 0, but with the eigenvector that we obtained originally. Okay, so what we're going to do is take a look at the same exact scenario we have here. 6, negative 18, 2, negative 6. But instead of augmenting it with 0, we're going to actually plug in the eigenvector 3, 1. Okay? Which, again, notice that the bottom row is a third of the first row, so that'll easily cancel out. Multiplying by a third, we get 1, negative 3, and now we have this half instead of 0 from before. So here we obtain that P1 is going to be exactly half plus 3 times P2. So this eigenvector is going to be, let's say P1 is let's make P2 0. That's probably the easiest. So if we let P2 be 0, then I just get 1/2 for P1. Okay, so then x2 is going to be C2, well, we won't put the constants in yet. We're going to have 3, 1, which is the same eigenvector from before, but now we throw in this extra t, okay? So this entire, like if you were to work all the way down to 3 solutions or 4, this first eigenvector, even though I'm changing the notation to 2, 1, is actually the same eigenvector that we obtained before, okay? So we're going to have 3, 1 t e to the negative 3t plus, and now we use our new eigenvector. This is what the K22 notation means, which is 1/2 0, and then that's e to the minus 3t. Okay? So, our final solution, we're going to combine x1 and x2 with superposition principle, so we get c1, 3, 1, e to the minus 3t. There's our x1, right? Plus c2, and now we'll throw in x2. Okay. And that's it. The rest is up to you. It's been real.